to you.
All right. Well, thank you very much, Terry. So I'd like to first begin by acknowledging that we're the messengers today, and that we have a big team that you can visit at the website listed on the title slide to look at the full listing of contributors to INCOR. So within INCOR, and I think this really goes for any community level resilience analysis, we begin by developing an integrated community model. And this is things like that you've been hearing about for an hour and a half already, but buildings, power networks, water, transportation. And then here you see the water and the power overlaid, and of course, dependencies and interdependencies, and those all have to be defined. And so this shows 15 flood archetypes that were developed for input into INCOR and are publicly available. And then the economy itself, how do we model something that maybe we can't see? That's the economy itself. And then also the social institutions, the households that you heard about, which essentially begins to represent the humans and that decision making. So INCOR stands for the Interdependent Network Community Resilience Modeling Environment. And here we start, as I mentioned, with the integrated community. And you'll hear more about the cloud computing system and the architecture of INCOR from Zhong Li in a few minutes. We then perform a damage and loss analysis, and as well as functionality aspects, and then an interdisciplinary recovery. And INCOR has a major focus on economics as well as social institutions. And then looking at, gives the ability to look at alternative actions to enhance community resilience and inform decision-making and planning. So the components, we look at hazards, as well as multiple and competing hazards, buildings, there's models for buildings, transportation networks, water systems, energy networks, communication, not a lot, but there's some under development. And then social systems, economic systems, as well as optimization strategies that you'll hear about in a little bit. And there's a number of test beds. We have even more than this under development now. 3 are available as Jupyter notebooks that are published and available as examples to run. So some of the key features of INCOR are that it's a computational environment, like several that you've heard about. It's not just software, but it allows for customization of analyses. So it allows the analyst to customize to exactly what they want to do, or to use defaults that are available. The resolution, it operates at the building and household resolution. Some of the household, I'll mention this shortly, it's synthetic household allocation algorithms that were developed by our Texas A&M team. And what that does is it enables combining infrastructure and social science algorithms for cross-disciplinary dependencies, because these decisions are made at the household level, as you heard Sharif mention in his presentation. Network systems, water networks, electrical power networks, these are modeled at the component level, so it provides linkage to household dislocation. And then models for functionality that are flexible. They can be user-defined based on probabilities of damage state, availabilities of other services, including social services. And so these can be user-defined, or defaults are available in the notebooks. And then computable general equilibrium models. These are available for the test beds that are published. And these are very complex models of thousands of interacting equations developed by our economics team here at Colorado State. And then the availability of a policy portfolio, and this will be coming in our next release. And this includes building codes, land use controls, land acquisition. And we'll be talking more about that in the policy session, since others were advertising, which is room 5, coming up a little bit in about an hour, actually. And then decision support, allocation of limited resources, budget, labor, toward mitigation and recovery efforts to meet one or more objectives. And of course, because we have the ability to step through time, you can look at the objective can be in the future for your simulation. And you can say, well, it doesn't have to be immediately following the event. And then the robust temporal and spatial analysis in core enables users to time step, as I just mentioned, rather than using trajectories. And so what this does is it allows you to consider the effects of policy that occurs during the recovery and test those policies out to implement policies at different points during a simulated recovery process. And then there's suites of fragilities available, and these include tornado, wind, and flood fragilities. And they're all in the form of, they do propagate uncertainty through the entire analysis. And then finally, two last features I'll mention, the advanced social science and socioeconomic algorithms. They predict household dislocation and relocation based on field study research. And this is research performed long before the Center for Hurricane Andrew by the Texas A&M team, Hurricane Ike, and then the center's Lumberton field study, which is a fairly robust longitudinal resilience documentation study. And finally, decision support based on core community resilience metrics. And this is coming in the next release. And this is core metrics, but they fit community specific goals and could be weighted if that's selected by the community. So just to give a quick example before we get to Zhong Li's demo, the housing unit allocation, you can see the references here, they're a little small, but this retains the intersectionality of socioeconomic characteristics, and it integrates with damage to structures and other critical infrastructure like water or electrical power. And the metrics connect impact of hazards on these population subgroups. So it can be renters, it can be homeowners, it could be a particular race, ethnicity. And this is based on publicly available US Census data. Another feature, and this is under development, it'll be, we hope, a first release in the late summer. We're integrating in core with the NIST Community Resilience Planning Guidebook or Playbook. And this, as you can see, this is this represents the conceptual architecture or structure of INCORE. Here you see we define our system, go into the damage, to the functionality, can loop through time for the recovery, all while kicking out metrics to do an optimization, and then of course visualization that you heard about in other presentations. And this shows which step of the 6 steps in the guide that these sections of INCORE align with. And so here's just some examples of a very early prototype, if you will, not even quite a beta, I'd say an alpha version here, just showing insignificant different levels of damage and the clusters within the guidebook. And so with that, I will stop sharing and pass to Zhong Li.
Thank you, John. Can you see my screen?
We can.
Good. So I'm going to talk about INCORE technology and platform, and also do some demo and talk about data in INCORE. This is a very brief diagram of how the INCORE structured. First of all, is built on the cloud computing system and technology. So currently NCSA, we have system called the Radiant, which is OpenStack and Kubernetes, the cloud system. We utilize the resources for INCORE. So on top of it, these components are developed and used right now. First part is I want to point out INCORE Web Services. This INCORE Web Services running on the cloud system to provide different services like hazard service, data service, fragility curve services, and authentication services, and geospatial visualization services. We have a slew of those web services provided through this component. And then that service is communicated by this INCORE library, Python library, which called PyINCORE. So PyINCORE is collection of the library of the INCORE researches. First part is algorithms and analysis that we implement in the Python, all the algorithm and data coming from the research groups under the center. And also it has a component to communicate with the INCORE services. So able to acquire hazard, acquire the data set, acquire the fragility curve, and things like that. And also PyINCORE-viz is the Python modules and functions to provide you some convenient way to visualize those outputs. And on top of it, we also do have InCore Web Tools, which is a lightweight web application that users are able to browse and search and download all those information served by InCore Web Services. And then we also provide a Jupyter Hub, which is a customized version of a Jupyter Lab we call InCore Lab. So user log in, and then it provides you Jupyter Lab environment that you are able to running this PyInCore and InCore Web Services and those things within this InCore Lab environment. So having said that, I'm gonna go right into the demo. Let me switch to my demo window. So this is a website. We call it maybe the landing page or a portal of InCore. So incore.ncsa.illinois.edu. Please visit the site. It has a lot of information here. The first quick thing is that you are able to see the current versions. We have also component as each versions. So if you know that, if you see that there is a 0.9.0 is a PyInCore library released, you can click on this link, changelog, it pointing to the GitHub repository. So that it explains very detailed about what we changed and those so far. And if you want to install this package, you can click on Conda package. It also pointing to the Conda Anaconda website that you can run Conda command to install PyInCore in your system. And most important aspect of this site is user manual. So InCore manual is a place encourage you to go first. It gives you the introduction of the system, and also it tells you how to acquire your free accounts. So you are able to sign up your account, and then this site shows you can follow this instruction step by step. It help you to run the building damage analysis with the existing data in our infrastructure. And mostly, most important also aspect of this documentation is each analysis. So if you go into each analysis documentation, it explains the what analysis about, and also what is input parameter, what is input data set, output data set, and also very important part is the code snippets. So you are able to cut and paste this code into your Python code. You're able to run right away, and also provide Jupyter Notebook as an example. You can run it and then test it out. So please navigate through this documentation. There's a lot of important information. And today I'm going to do demo for one of the Jupyter Notebook or testbed notebook. So as John explained, we published these 3 testbed as a Jupyter Notebook: Galveston, Joplin, and Seaside. So on this page, you can also find the zip file that you are able to download the Jupyter Notebook in your local with the PyInCore installed. You are able to run this Jupyter Notebook and also read about each testbed. So this testbed page currently generated automatically from the Jupyter Notebook. So you can see some code and also explanation, scientific explanation and discussions and things like that. So this is a static page, but if you download the Jupyter Notebook, you are able to run and reproduce this result again on your machine. So let me switch to Jupyter Lab environment right away. So what I did is this is an InCore Lab environment. Some of you known as a Jupyter Lab, but we customized a little bit to add some of the menus here. So you are able to access to different apps and then documentations. So for example, if you go into the data viewer we have, you are able to automatically log in and then look at the data viewer. You can search on here like Joplin building data, that it shows all the Joplin building data available. Right now, you see a lot of data set because I'm in the admin account, so I'm able to see some of the other data set here. But when you log in to do it, usually you are able to see publicly available data within this. And also you can look at, let me go to fragility curve, maybe you are interested in. So you can look at, it also display some of the data available here. So if you click on this, it provides the metadata, and also click on the preview, it shows what the fragility curve looks like. So this is the application. You navigate and browse through those web services we have. So having said that, this is the Jupyter Notebook that we already published, Joplin testbed. So you can see that the exact Jupyter Notebook here, I'm gonna run some of it in the live. So you can see some description about what the testbed is about. And then this is a part that you can import all those Python packages we need. And you can see this line right here. This is the command line that connect to the web service, in-core web service. So if you are not logged in, it asks you the username and password, and you can log in. It already done. Then it actually read the token in your system so that it detected right now. And then we're going to look at quickly the tornado we're going to work with. So this is a Joplin tornado already in the system. So you see the tornado path of Joplin tornado, and each different color represent the different EF rating, which is associated with the wind speed. And then this is a description of some of the building inventory we already have for Joplin, different types of 19 RT type of buildings, which is tied to 19 fragility curves. And also, now you can able to look at the fragility curve available in our fragility curve service. So this code shows that what it does is it has the ID of the build, mapping ID, which is a fragility mapping ID, and then going through that fragility services to display information. It only displays just 3 of them among the 19. So you can see display this chart using Python library. So having said that, using the fragility curve and inventory, now you are able to run building damage analysis. So you can see right here, we define this a tornado, and then there's hazard ID. These IDs you are able to acquire from the apps. So I can show you quickly here. If you go to hazard viewer, and you can also filter for the tornado. And you can see some of the tornado available here. So you can click on it, and then you can see here called the copy ID. If you click the copy ID, it copies on the clipboard, and you are able to use it on your Jupyter notebook like this. So this is all this ID is about, so how you can interact with our web application and your code. So define the hazard and also import the building damage analysis. Now you defined building inventory data set and fragility curve, and then set some other aspect here, and then set it up. And then if you run here, it runs now. So it took a little time. While it's running, I can explain a little bit about fragility mapping. So fragility mapping within in-core system is the idea about how to map infrastructure to the fragilities. As you know, there are many fragility curve available for building in case. Then we're looking at the building attributes and its structure types or archetype or age of the building. And based on this criteria, we create a mapping that what is the best fragility to map to that infrastructure. So that's a fragility mapping. And we already created those things in our fragility service. So user able to use those mappings as a default. However, if you want to create your own mapping, you can create a local fragility mapping, and using our specification, you can run those mapping for your damage analysis. So now we finished the running, so you can see that output here. So GeoID is the way we can recognize unique each buildings by unique ID, and it shows the limit state 0 and 1 and 2, and the damage state 1, 0, 1, 2, 3, 4, 3. So now look at quickly, let me sort the DS3, damage state 3, and the descending orders. You can see that there are certain buildings has 1.0 probability and things like that. And you can also look at quickly statistic summary of this column. There is right now about 28,000 buildings here, and some of the mean value, standard deviation, and things like that. How about let's look at the buildings who has a greater than 0 damage state 3, and there is a 7,831 buildings among 28,000. And also, if you want to visualize on the map, you are able to do that. We have some convenient method provided from our visualization package, and you can run it. It'll generate the map plot using right now DS3. So you can see here that there's a building damages happens along the Joplin tornado path right now. So I'm not going to run another analysis. There's a lot of analysis shown in the Jupyter notebook. I'm going to go through quickly. So it does also electric power facility, especially the substation damages. And you can see some output here. And then power facility for the poles damages. And then using those things, there is a Monte Carlo simulation to training this building damages, and also this electric power facility substation and pole damages. And using those outputs, you are able to also calculate some of the building functionality probability here. So this is the code that does the building functionality building functionality analysis. So after that, I can just quickly show you some of the outputs here. So maybe remember that what happened in the building damage distribution in the map. And then this one shows that a little bit of different map here. So look at here. You can see that there's a more building functionality is damaged compared to the previously the building damage itself, because the building functionality looking at the relationship with the electric power facilities. So that impact is actually spread through more than other places here. So having said that, I'm going to move on to the another part that I think that many people are interested in is economic analysis. So currently we work with a group of researchers in Colorado State who are developing CGE model. It's a computational general equilibrium model, which is based on the microeconomics theory of supply and demand equilibrium model. So they construct this model for the Joplin and Seaside, and then we're going to release out more of these models. So right now, this one does is running a CGE model for Joplin based on some of the damages happening in the building. So you see the code right here called the capital shock analysis, which means that it tries to generate how much capital shock to the economic system from building damage. So it does that analysis, and then it's able to run the capital shock analysis, and you can see that some of the shock happening to different sectors within Joplin, economic sectors in Joplin. And then we are able to now run CGE model using these capital shocks. So some of the input data set, you can see a lot of them. This is mostly related to the economic input output model and then social accounting metrics model built for the Joplin. And after that, you set it up some of those inputs again. And then now it's almost ready to run. So now you are able to run this, and you're able to see that it's running in real time here. So you can see this optimization solver running behind and then running the different iterations and then try to find the equilibrium right now. Okay, now it's finished the running. So now we're able to looking at some of the domestic supply happening here. So the first column DS0 is basically baseline before the shock, and the DSL is after the shock. So you're able to see that depending on some sectors, those domestic supply has been decreased because of shock. Similar thing, we could do that looking at gross income for the household groups. You can see some changes before and after shock. And then there's other visualization for some of the demanded things. You can look at it too. And then another analysis also interested in by a lot of people here is population dislocation analysis, which does is that try to identify how many population, how many people from each household need to be evacuated or not doesn't need to be evacuated. And so it comes with the analysis called population dislocation model. So I'm going to quickly run this. This is my last part of the demo. And then run the analysis. And then you will see the output had the last column at the end of the analysis. So you can see right here, each building, you can see the dislocated or not. So it's false or true. So it's able to distinguish those information right here. So let me finish my demo here so we can get some more question afterwards. I'm going to continue my presentation, go over some of the aspect of the data. I believe also we provide you 4-page premier writing about INCORE, so you can look at more detailed information there. So I'm going to go a little bit quickly on this aspect. The INCORE provide the data on the 3 different services. One is obviously hazard, and then DFR3 services, which provide the equations or curves and functions for damage, functionality, repair, recovery, and restoration. And the data service, the one also provides you the information or data about built-in infrastructure inventory, census data, economic data, and then also in various formats. And along with this data set, we also have a metadata specification. So there's metadata for the fragility curve, metadata for the hazard, metadata for the data sets. All of them is in the JSON spec, and we also, all the specs are compliant with the JSON LD format. And so you can look at if you log into our site, if you click on the data set or any hazard and things like that, it has a button called download metadata, and it downloads the JSON metadata for each of the data set. So currently, InCore Data Service has access control, which means that we distinguish the data for the public and data for the center and data for your private use. So this is called a space. And when you have an account and you log in, automatically you are able to access to two public space. One is called InCore, the other is Argo. So currently within that public space, these are the data set we are serving. It's obviously increasing every release we have. So 395 data set, among the 60% is related to the hazard data sets. And also there's 1,092 fragility curves that covered earthquake, tsunami, flood, tornado, and hurricane wind and hurricane surge and wave. And also there's 17 earthquake hazard, 3 tornado hazard, and 12 tsunami hazard with a different intensity and different occurrence in the probabilistic way, and then 2 hurricane wave and surge hazards. And the last part about the data is data management processes, especially related to this publicly available data we currently publishing. So there's 2 important aspects here. One is when the data comes in, then we looking at this data is validated with our data type. Data type usually means that it's a schema. And then if that validate and the data is good, then we upload to the system and share. But now in some cases we don't have the data type, then we work with the research scientists and researchers to define the schema in our system, and then also upload in our system. So this diagram shows that aspect. The summary here about some of the resources available. There's a manual out there. I already showed you that there's a link here, and you can sign up account in that link, or you can go to the manual. It shows you the link there too. And you can install your PyInCore and PyInCore Viz library on your local right away using this command. And also if you're interested in source code, there's a GitHub account, a GitHub repository you can look up. And if you have any question, installation and usage, you can send us an email in this email address. John?
All right, thanks, John. And in the interest of time, I'll just close by saying that we have a webinar that'll be scheduled for April 22nd, and we'll focus on InCore, and then a scientific user workshop open to anybody that wants to learn more and how to use it. That is being detailed out, but it'll be scheduled for May 21st. And the next slide, please, John. And obviously, I want to acknowledge NIST and thank you. And you can get more information at this email address, which then forwards to me. Thank you.
Okay. Thank you, John and John. We are running a little behind, so I just want to say there were a number of comments about the fragilities and a question about vulnerabilities. So maybe if you could just briefly explain how they're available through databases, and then we'll go on to the next presentation.
John, I think that's for you probably better.
Yes, I try to think what's the best way to explain.
I think one thing, if it depends on the fragility, a lot of them are in published literature. So if you look in InCore, you can find where they are if you're just looking for the log normal parameters. But if you're looking for the actual data, then John.
Right, and another good example is I'm currently thinking that our Jupyter Notebook example. I think Seaside may be a good one you can look at. So because the Seaside using probabilistic hazard for tsunami and earthquake. So that may be a good example that how the InCore use to come up with a vulnerability mapping there. So maybe that can be a good example.